Buenas tardes. So each of those circles that you're seeing here represent a star about which we found another planet. It wasn't only a little bit more than 20 years ago when the only planets we knew of were the ones in our solar system. And in this short period of time, thousands of planets have been discovered. And astronomers now think that every star in our galaxy has at least one planet. And even more exciting than that is the fact that we have found planets that are the size and shape of the Earth, hundreds of planets that are Earth-like. This has been transformative for astronomy. And what I want to talk to you today is about the next step. Now that we know there are Earth-like planets about other stars, how do we examine them and characterize them and discover if they can harbor life? I'm going to tell you about the technology being developed in NASA and in my lab to go in a space telescope to do just that. But first, let's look a little bit at how all of these planets have been discovered. Every planet that has been found so far has been discovered by one of these two methods, radial velocity or transit photometry. In radial velocity, on the left, what you see is we look at the star, not the planet, and we can measure the speed of the star as it co-orbits the planet by seeing how its color changes as it goes around in the orbit. From that, we infer that there's a planet, and we can actually get the mass of the planet. In transit photometry, we collect light from the star, and we see this characteristic dip in what we call the light curve as the planet passes in front of the star and blocks just a small amount of the light. And from that, we can determine the orbit of the planet and the size of the planet. This is actual data from radial velocity and transit measurements. The radial velocity measurement you're seeing is for a planet orbiting our closest companion star, Proxima Centauri. It's a roughly Earth-sized planet. And the transit curve you're seeing was discovered by the Kepler telescope, and that was also an Earth-like planet in an 8-day orbit. So 1 year on that planet is only 8 days. So astronomers have continued to be surprised by the diversity and somewhat peculiarity of the planets they're finding. And none of them have been like any in our own solar system. So the question we ask then is what do we need to know next? Now that we know there are these Earth-like planets that so many have been discovered, what do we need to know to be able to determine if there might be life, if these could harbor life, like that slide I showed you earlier? Well, the first thing we need to do is we need to know if it's in the habitable zone. The habitable zone about a planet is the region where the temperature is just right for liquid water. Closer to the star, and water boils away and you can't have life. A little further away from the star, it freezes out into ice and you can't have life. Liquid water is a necessary element on the planet for it to be able to harbor life. And the really exciting thing is we have found many, many planets in the habitable zone using those methods that I just showed. In fact, astronomers now think that perhaps as much as 1/5 of all stars in the galaxy has a planet roughly Earth-size in the habitable zone. So remember that first slide I showed you. There's that planet that was discovered by Kepler, the first one, only 4 years ago, an Earth-sized planet in the habitable zone. It's in a system with 4 other planets, and you can see that that habitable zone is actually much closer to the star than the planets in our solar system, because the star is actually a cool M-dwarf. It's a much dimmer star, and so you have to be closer for it to be hot enough to have liquid water. Remember Proxima Centauri. So the Proxima Centauri, along with Alpha Centauri, are the closest stars in the galaxy to us. This is an image taken from Chile. So remember I showed you Proxima Centauri b that was found through radial velocity. That's the Earth-sized planet orbiting Proxima Centauri. And don't get too carried away with these images. Artists love to paint pictures of these planets. We have no idea really what this planet looks like, but maybe it looks something like that. But we do know that it's in the habitable zone of Proxima Centauri. And again, Proxima Centauri is a very dim star, so that habitable zone is well within the orbit of Mercury in our own solar system. But nevertheless, we're getting quite excited. And we're finding systems totally and completely different than our own solar system. This was discovered just last year. This is the TRAPPIST-1 system, where there are 6 Earth-sized planets crammed into this little habitable zone way inside the orbit of Mercury. And the really exciting thing about the TRAPPIST-1 system is these actually aren't just artists' impressions, because in this system, it was found through transits, and we were able to look at the changes in the orbits and figure out the mass. So we know both the mass and the size of the planet. So we can guess that it might be all water, it might be all rock, depending on the density of the planet. So it's amazing how much we've learned about these planets. The next thing you need to do if you're going to figure out whether there's life on these planets is you need to directly image the planets. Those other techniques are called indirect techniques, and they collect light only from the star, and we infer the presence of a planet. The next thing to detect life is we need to get light right off the planet itself. So this is NASA's famous pale blue dot picture. This was taken by the Voyager spacecraft as it exited the solar system 6 billion kilometers away. And you can see this small dot that the arrow is pointing at that's looking back at the Earth. We need to take images like that of exoplanets. If we can do that and get light right off the planet like that, then we can actually look at the spectra of that light, which was supposed to have come up. This is looking at the color of the light coming off the planet. And by looking at where there are these characteristic dips in that curve, we can tell whether there's oxygen on the planet, ozone, water, methane, carbon dioxide. We can see if the sky is blue. We can even see potentially if there are green plants on the planet doing photosynthesis. So by getting light from the planet, we can learn an enormous amount and hopefully figure out whether there might be life actually on that planet. So this plot shows you all of the planets that have been discovered to date about other stars. And one of the things you see is all the planets are either much smaller than the Earth and very close in, or extremely large relative to the Earth and fairly far out. And this has nothing to do with the universe. This has to do with the biases and the methods that we're using to detect the planets. And we've only directly imaged a very few. Those are the planets that we've directly imaged from the ground. Many of those were imaged from telescopes up in the mountains of Chile. And what you see is the only planets we've actually taken light from are extremely large, much bigger than Jupiter, and very far away from their star. What we want to do is we want to find and image planets down here, where we haven't seen anything yet. That's where our solar system lies. That's where we would find an Earth-sized planet in the habitable zone of a star like our own. And the only way we're going to do that is through direct imaging. But direct imaging of small Earth-like planets in the habitable zone is really hard. And so what I'm going to do next is show you why it's really hard and why we need these special technologies to do that. So to understand that, let's do a thought experiment. Imagine taking the Hubble Space Telescope, turning it around, and moving it out to the orbit of Mars and looking back at Earth. So this is an image, a simulated image of what Earth would look like through the Hubble Space Telescope from Mars. And it's pretty well resolved. We can see continents and oceans and clouds, a little blurry because it's from a fairly small telescope really far away, certainly compared to the ones up in the mountains of Chile. Now let's move it 10 times further away. And here we are at the orbit of Uranus. And now it's a much smaller image, so you can barely make out the moon, but you can still see a little bit of the continents and clouds and oceans. 10 times further away again, and here we are at the edge of the solar system in the Kuiper Belt. Remember when I talked about the Voyager spacecraft looking back? That's the pale blue dot from the Hubble telescope out at the edge of the solar system. We've lost all ability to resolve the planet itself. We go 10 times further away again, and here we are in the Aurora cloud, and we're starting to see the sun enter into the field of view and block our ability to see. We can still see the planet, but you can start to see the sunlight leaking in. Finally, 10 times further away again, and here we are at Alpha Centauri, our nearest neighbor star. The planet's gone. All we're seeing is the sun. That's what someone living on that Earth-like planet around Proxima Centauri would see if they pointed their 2.5-meter telescope back at us. And what you're seeing is diffraction of the starlight inside the telescope. It creates that big blob in the center and all those rings you're seeing, and it totally swamps our ability to see the planet. That's why it's hard. We have to somehow remove all of that starlight. We have to do something to our telescope to get rid of that corrupting light and let the planet shine through so that we could take spectra. So there's two ways that my colleagues and I in the field are looking at doing that. So what's the solution? You have to go into space. The atmosphere will totally mess things up on the ground, and you have to use either a chronograph or a star shade or both. These are the two leading technologies to image exoplanets. And I'm going to tell you about how both of those work, and we'll start with a chronograph. A chronograph was invented by Bernard Liot in the 1920s to look at the solar corona. He was tired of traveling around the world to solar eclipses to do that, so he invented the chronograph so he could do it in his telescope in the Observatoire de Paris. And so what I have next is a video that NASA produced that will show you how a chronograph works. It does a much better job than I can. It's narrated by my friend Nick Ziegler from the Jet Propulsion Laboratory. And remember, chronographs are in use today on almost every ground telescope, and even Hubble has a chronograph. So let's learn how a chronograph works.
distant star is orbited by two planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the two planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
So that's how a coronagraph works. I have some of those deformable mirrors in my lab, and there's actually systems like that on several telescopes on the ground, two here in Chile. We call that digging a dark hole around the star. And this is an image taken from the Gemini telescope using the Gemini planet imager of a Jupiter, actually one of those big planets, much bigger than Jupiter I showed you earlier, orbiting the star 51 Eridani b. And you can see that dark center where the coronagraph was. And as I said, this was taken from the Gemini telescope up in the deserts of Chile. But this is the best we can do on the ground. So to get Earth-like planets, we have to put a coronagraph into space. And that's exactly what's happening. So that's the WFIRST telescope, the Wide Field Infrared Survey Telescope. NASA is now actively involved in. I'm responsible for the coronagraph. It will have a coronagraph on board. It is scheduled to launch in roughly 2025. And that coronagraph will be able to image Jupiter-sized planets, which is incredibly exciting. It'll be the first time we've ever done that. Even more exciting is the prospect of being able to get Earth-sized planets with this telescope. And to do that, what we're hoping is that we'll be able to launch a starshade with WFIRST. So in my remaining time, I want to explain how a starshade works. So a starshade was first suggested by Lyman Spitzer in 1962. It was inspired by a solar eclipse, like you're seeing here. And the idea is here where the moon is passing in front of the sun, blocking most of the light and casting a shadow. It's the same thing. If I put my thumb up, I can block that big spotlight by putting my eye in the shadow cast by my thumb, and then I can see much better. This is the same idea. The moon is casting a shadow onto the surface of the Earth. If we can put a telescope in that shadow, no more sunlight, and we can see the dim corona around the sun. So what Spitzer suggested is let's do that in space. Let's fly a big disk out in space, put it in front of a star, block most of the light, and then we can see the dim planets in front of it, next to it, if we put a telescope in that shadow. The problem is that doesn't work because you get diffraction around the star shade the same way you get diffraction in the telescope that I showed you earlier that messes you up. But Spitzer figured out the solution. If I can feather the edges, make them a special shape, then I can control diffraction around the star shade and dramatically improve the shadow, reduce the amount of light, and lo and behold, you can see the planets orbiting the star. So that's the challenge, is to build that. And it seems formidable, but my colleagues and I at JPL have been working on this for about the last decade, and we have a wonderful mechanical engineering concept for how one does just that and launches it into space. So that screen needs to be about half the size of a football field, and it flies about 50,000 kilometers away from the telescope. the video's not actually working so well, so I apologize for that. But this gives you the idea that the petals are wrapped around a central hub, and they unfurl, and then the whole thing expands until you get this giant 40-meter star shade, which then moves in front of the star, blocks the light from the star, and boom, you can see the planets that are orbiting it. So what you would see, if that was working, is a prototype of this that we've built. Those petals have to be built very precisely, and I have a video of an experiment that we did where we actually expanded a half-size star shade, and the petals all have to go to exactly the same place every time, and they did within about 1/10 of a millimeter. So we've been working on this actively, my colleagues and I at JPL and other institutions, to show that we do understand how to make a star shade and how to meet requirements. And so the exciting thing is that what we're hoping is that we'll get approval from NASA to fly a star shade with that WFIRST telescope, and that will give us the capability to image an Earth-like planet. So remember Proxima Centauri? So that's a picture of Proxima Centauri taken from the Hubble Space Telescope. And you can't see anything about it, but if we can get a star shade up in space and put it around a star that looks something like Proxima Centauri, where we may know that they're Earth-like planets, we might get a picture that looks something like that. So that's a simulated image of our solar system from a Hubble-sized telescope past a star shade. And you can see Jupiter, Saturn, Uranus, Mars, and right there, close in next to the sun, is the Earth. And so we're incredibly excited about being able to do this. NASA is actually actively sponsoring now studies to look at the next generation of telescope that would come after WFIRST. There we go. So HABEX and LUVOIR. HABEX would be a 4-meter telescope with a big star shade, and LUVOIR would be a 9 to 15-meter telescope. These are giant telescopes, some bigger than anything on the Earth, that will fly into space. And if these things happen, and I'm on the study teams for these, we might be able to find hundreds of Earth-like planets around all of our neighboring stars in the galaxy and characterize them and really understand whether or not life exists outside of our own planet. And perhaps someday soon, after that, we could go there. So this is the Breakthrough Starshot concept from the Breakthrough Foundation, where they want to take thousands of small cell phone-sized cameras and send them out to Alpha Centauri at near the speed of light so we could take close-up pictures of the Earth. And what we're hoping is what they're hoping is they can have all the technology for this ready by the 2040s. So in my children's lifetime, there's this possibility that we'll finally go to our nearest neighbor star, see an Earth, image it, characterize it, and understand that we're not alone in the universe. And to me, that's just a profound event to even contemplate and humbling to think about. So thank you.